right. Now we shall start what is known as a new process, that is called the birth and death process, right. The birth and death process is an integral portion of any queuing theory, and for any queuing theory analysis we need to look at the birth and death process. So, birth and death process act as the foundation of commonly used queuing models. Here the births can be as an equivalent to arrival of a customer or job, and death could be equivalent to the departure of a served customer or job. So, assumptions: given nt equal to n, the time until the next birth, that is Tb, is exponentially distributed with parameter lambda n. What is lambda n? Customer arrival according to a Poisson process. Why lambda n? Because in a general way we are making an assumption that the arrival is dependent on the state. So, suppose n equal to 0, then lambda 0 is different from n equal to 1, that is lambda 1. What is lambda 1? If the state is 1, that means there is one customer in the system, then number of arrivals will be determined by lambda 1. Then the remaining service time Td is exponentially distributed, is with parameter mu n. Similarly, mu, that is the service rate, is also dependent on the what is called the current number of people in the system, that is called n. Now, Tb and Td are mutually independent stochastic variables, and state transitions occur through exactly one birth or one death. Because last class we have seen that the exponential and so called process and the Poisson process, they have the unique thing that in a short period of time there could be only exactly either one birth or there could be exactly one death. So, that is about the birth and death process. Now, you see, we have already told that the usually whenever a queuing system begins, in the very first we have what is known as a transient period. During the transient period, the queue system does not stabilize. Till the queue system does not stabilize, we cannot really think of an equilibrium condition, and we cannot really think of a queuing process to begin, right. The kind of analysis that we do in a queuing process, we cannot do until unless the queuing system comes to an equilibrium. So, that moment the queue system comes to an equilibrium, at that time we can analyze very easily by simply drawing a rate diagram, right. So, what is a rate diagram? Look at this rate diagram very carefully. This describes a birth and death process. What are these 0, 1, 2, n minus 1, n plus 1? They actually determine the system state. Say a system state is 2. What is the meaning of this? That means there are 2 customers in the system, right. There are 2 customers in the system. Now, how a system can have 2 customers? If there are, let us say, 3 customers, suppose n equal to really 4, then if there are 3 customers, then one customer can get serviced. When one customer gets serviced at a particular rate, what will be the rate? That rate will be dependent on the state. So, we call it mu 3, right. In mu 3 rate, a person will be serviced and it comes to 2. Similarly, how does a system state is 1, how can it go to system state 2, right? There is another way, that if one customer arrives and joins the queuing system. So, one customer arrives and joins the queue system, then the system state become 2. So, that is what a rate diagram basically determine. So, you can see very simple, you have to simply draw the states and you have to just draw these arrows in such a manner that from 0 customer arrives, it becomes 1, another customer arrives, it becomes 2, another customer arrives, it becomes 3, like this, so on and so forth. Now, how it is general? Because assume a multiple server. If the multiple server is there, then it is not necessary really that you have these values of lambdas and mu's will change. But although the values of lambdas and mu's will change, since the transition can occur only one at a time, the rate diagram will still be valid, right. So, this is about the essential idea that how birth and death processes can actually be modeled with the help of a rate diagram. Now, let us make some very basic assumptions and consider the simplest model, that is so called MM1 model. In an MM1 model, what happens? We have these assumptions. What are they? First of all, we assume an infinite input space and independence between arrivals, right. That means, arrival of one person is independent of another person arriving. The arrival process is Poisson with an expected arrival rate lambda. Independent of number of customers currently in the system. A single queue is formed of no restriction on its length. Also assume no reneging or balking or such special cases, and let us simply assume the queue discipline to be first in first out. The service mechanism consists of a single server with exponentially distributed service times, where mu is the expected service rate when the server is busy. So, all of these put together, this is the steady state analysis. In the steady state analysis, the following balance equation must hold for every state n. The rate in equal to rate out, right. That means, the mean entrance rate equal to mean departure rate, and also the sum of all probability states should be equal to 1. So, sigma I equal to 0 to infinity pi equal to 1. Then let us look at the balance equations. In fact, these balance equations can be obtained from these rate diagrams. How it is obtained? Let us see for an MM1 model. Let us draw it here also, then it will be understood easily. Let us say, and we have an MM1 model. Now, for an MM1 model, these are the system states 0, 1, 2, then we can draw n minus 1, n plus 1, right. From 0 to 1, if there is an arrival, similarly here, and on the other side, and since it is a simple MM1 model, then all these are mu's and all these are lambdas, right. So, this is our rate diagram. Now, look here, what is the balance equation says? Go back there, let us put those equations before us. Number 1, rate in equal to rate out. Number 2, sigma pi I equal to 0 to infinity equal to 1. Only 2, they are very simple, only 2 simple principles, and we have nothing else. So, if that is so, then how do we make the balance? You see, at state 0, what will be the balance? You see, what is going out and what is coming in. Going out is lambda and that value is P0. So, lambda P0 equal to mu P1, right. So, very simply we can write How do we get? This one is the probability at here at P0. So, what will be the rate? Lambda times P0, and here the state is 1, probability of the system having 1, and mu is coming out. So, rate in equal to rate out, we simply can write lambda P0 equal to mu P1. So, if we do that, then from here we can write P1 by P0 equal to lambda by mu. All right. So, very simply we can make this balance. Let us make one more balance, that is at state 1. What is the balance at state 1? What is coming in and what is going out? So, rate in, what is the rate in? Rate in is lambda P0, this is one rate in. What is another rate in is mu P2, mu P2, and what is going out? Going out is lambda P1 plus mu P1. Is it all right? So, these are the things that are going out. So, from here what can we make out? We can make out is mu P2 equal to lambda plus mu P1 minus lambda P0. Is it all right? So, you can further simplify, this gives P2 equal to lambda plus mu by mu P1 minus lambda by mu P0. Is it all right? But look at the first relation, this is the first relation. From the first relation we can say P1 equal to lambda by mu P0, is it not? This can be derived from the first relation. Now, here we have a lambda by mu P0. So, we can write therefore, lambda plus mu by mu P1 minus simply P1. All right. So, basically it is minus 1. So, here it is lambda by mu P1 plus 1, you can simplify, it is lambda by mu P1 plus P1 minus P1 equal to lambda by mu P1. So, basically we got two very interesting relations. One, we have got P1 equal to lambda by mu P0, P2 equal to lambda by mu P1. So, very interestingly we have been able to really obtain two of the very simple but fundamental relations. So, look here, this is how we have been able to now generalize. How do we generalize? That P1 equal to, this is not here, okay. So, anyhow, the advantage that we can get is we can actually put this in that format. In that format, what is that format? That P1 equal to lambda by mu, because all lambdas and mu's are same. So, P1 equal to lambda by mu P0, P2 is lambda by mu P1, and Pn is again lambda by mu Pn minus 1, right. So, when you add them all, right. So, you can see, therefore, you can write that in another way, since this is happening, that let us say we have got, say let us put lambda by mu equal to rho, right. So, we have got P1 equal to rho P0. We also know P2 equal to rho P1 equal to rho square P0. P3 equal to rho P2 equal to rho square P1 equal to rho cube P0. So, like this it goes. Supposing we put them all together, if you put them all together, then P1 plus P2 plus P3 plus P4 plus dot 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 equal to 1 plus rho plus rho square plus rho cube plus dot 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 P0, right. So, all of these relations they can be obtained in this format, but what are these? This one is, if you really compute, then you can add P0 this side also. So, you can add P0 both sides, you can add P0 also here. Moment you add P0, then it will be plus P0, which basically means 1 will go inside. So, it will be 1 plus rho square plus rho cube plus etc. Now, all of these terms, what is it? It is nothing but 1, is it not? So, all of these adds to 1, right. So, this side is 1 and this side is this term, since rho is less than 1, because you see we have already told that lambda should be less than mu. Lambda is less than mu. If lambda is less than mu, then rho should be less than 1, because rho is lambda by mu, because for steady state the service rate should be higher than the arrival rate. So, if that is so, then rho should be less than 1. If rho is less than 1, then what is the sum of these quantity? 1 plus rho square plus rho cube etc. This is nothing but 1 by rho. So, this becomes P0 by 1 minus rho, right. So, in simple terms, from here we can make this P0 equal to 1 by rho. Okay. So, now we have got P0. Once we get P0, we can compute P1. P1 equal to rho times 1 minus rho. P2 equal to rho square 1 minus rho. In simple terms, Pn equal to rho to the power n 1 minus rho or rho to the power n P0. All right. So, these are the essential terms that we can actually compute, and we can actually therefore see all these relations, that is P0 equal to 1 minus rho, Pn equal to rho to the power n 1 minus rho, Pn greater than equal to k is rho to the power k, and similarly this formula can also be obtained, that L equal to rho by 1 minus rho. So, I am not showing it, but let us assume, but we can show it also in detail, that is L equal to rho by 1 minus rho, right. L equal to rho by 1 minus rho. Now, you can use Little's formula. What is that? Since we know L equal to lambda W, then, and what will be the W then? The W will be then L by lambda. So, it becomes 1 by lambda rho by 1 minus rho. What is rho? Rho is lambda by mu. Okay. So, this is how you can also obtain what is known as W, right. Then you can also obtain LQ and WQ. So, WQ will be W minus 1 by mu, right, because W equal to WQ plus 1 by mu. So, it will be 1 by lambda rho by 1 minus rho minus 1 by mu. So, all these calculations can be definitely done, and simplified forms can also be written. So, look at the slide here, you can see L equal to rho by 1 minus rho, LQ equal to coming out to be rho square by 1 minus rho, or in simple terms L minus rho, and W equal to L by lambda, that is 1 minus mu minus lambda, and WQ is LQ by lambda, that is lambda by mu into mu minus lambda. But anyhow, all these are not required, we can do some simple calculations on the basis once the formula is known. One very important interpretation is required here. What is that interpretation? See, we have already seen that P0 equal to 1 minus rho. And what is rho? Rho is lambda by mu. You see, P0 means probability of nobody in the system. Right. So, if P0 is probability of nobody in the system, which is 1 minus rho, then what is 1 minus P0? 1 minus P0 is probability of somebody in the system. See, it is the other side of the picture. One side of the picture is probability of nobody in the system. So, all these are for MM1 Q, right. So, probability of nobody in the system is P0 1 minus rho. So, probability of somebody in the system is 1 minus P0, and what is the value? 1 minus P0, if P0 equal to 1 minus rho, then 1 minus P0 equal to rho. So, that is the beauty of the thing, rho equal to lambda by mu equal to 1 minus P0, which is nothing but probability of somebody in the system. And this is called the utilization nothing but the utilization of the system, right. So, actually rho or lambda by mu really determine the utilization of the system, and in particular case for MM1 it also signifies 1 minus P0, that is the probability of somebody in the system. Is it all right? So, you know what we basically can therefore look at is that for an MM1Q, you know we can see the system parameters, and all these system parameters they have something very unique, and that unique is that we can have the you know all the system parameters they are based on some simple calculation on rho and 1 minus rho, that is 1 minus P0, that gives you the system utilization, right. So, let us quickly review what is it that we have done in this particular thing or discussion on birth and death process. Once again, if you look at the birth and death process, very quickly let us review this, because it is so important topic, and this rate diagram we shall keep using again and again. Let me again reiterate, the rate diagram of a birth and death process which is shown here is only useful when the system is in a steady state. If the steady state is not reached, that this rate diagram cannot be used, right. Rate diagram can only be used when system comes into the steady state. But does the system comes in the steady state right in the beginning? First of all, in most situations where you know arrival rate is not lower than the service rate, the steady state does not happen, right. There is no steady state. Suppose you go to a queue where there is only one service person and that too servicing at a very low rate, and people are coming in a continuous manner, then what is happening? There cannot be any steady state. The arrival rate is much higher than the service rate. There is no steady state, no such rate diagram of a birth and death process can be constructed, right. So, simple advice, queuing system is not applicable here. Only thing that you can do is you can try to achieve a service rate which is higher than the arrival rate. Till you achieve that kind of service rate, there is no point of talking about queuing systems and queuing system analyzing. It is definitely a queuing system, but it is in the transient state. The steady state has not reached. So, precondition for reaching steady state is that lambda should be less than mu, or in other words the utilization rho which is should be lambda by mu, that should be less than 1. Is it all right? That is the first requirement. Once that is possible, only then the birth and death process, the rate diagram can be constructed. Now, once the rate diagram is constructed, you can see that the rate diagram shows the states of the system, that is 0, 1, 2, etc., etc., and they are state dependent. So, arrivals that happen at state 0, because we are also making an assumption that there is a single, there is exactly one, the state transitions occurs through exactly one birth and one death. So, these actually happens and these are the rates. Once we know that in an MM1 queuing system, which is shown by this diagram, then you can see that from the state 0 there is an arrival through this lambda process, then it can come to state 1. Then if there is a service, it comes back to 0. Then what we did? We did what is known as the steady state balance equations. The balance equation is rate in equal to rate out, mean entrance rate equal to mean departure rate, and also the sum of all probabilities should be 1, right. So, then what we did? We have made these computations. Let me show once again. Look at this rate diagram. Then in this rate diagram, what we did at state 0, we put lambda into P0, because that is where is the probability, and equal to mu P1, right. And from here we got P1 equal P0 equal to lambda by mu, and therefore P1 equal to lambda by mu P0. At 2 we have written mu P2 equal to lambda plus mu P1, because that is what is happening, that mu P2 lambda P0 at state 1 lambda P0 plus mu P2, that is lambda P0 and mu P2 they are arriving, and lambda P1 and mu P1 they are leaving, right. So, if you put that, then you can compute mu P2 equal to lambda plus mu minus P1 minus lambda P0, from where if you simplify, then you find that you get P2 equal to lambda by mu P1. So, those things are written here, rate in equal to rate out, sigma Pi equal to 1, P1 equal to lambda by mu P0, P2 equal to lambda by mu P1. So, all these calculations further, what you can do, you can see that since lambda by mu equal to rho, then you can write P1 equal to rho P0, P2 equal to rho P1, P3 equal to rho P2, these will follow, and then you can add both sides and you can get a simple calculation that this side becomes 1, because sum of all probabilities are 1, and this side is that sum will be 1 by 1 minus rho. So, P0 by 1 minus rho, and then from here you can compute P0 which is 1 minus rho, right. So, and then from here you can also compute Pn equal to rho to the power n 1 minus P0, all right. So, from here the different parameters like L, LQ, W, WQ can also be computed. right. In our next class, we shall again see all these parameters, you can solve some problems and carry on from there, right. So, thank you very much.